All right, so today we're going to do what's called a synthesis problem. There's one of these on the final project. Probably won't be on exam 3, unfortunately. We're coming in, or if it is, it'll be really simple. So the idea is I guess that doesn't really, this would be, okay. So when you have a synthesis problem, and this is starting to be pretty realistic to what an organic chemist needs. I was going through this with a project of my own just this morning, not these molecules, but like I need this compound. All right. So what I have to start with is this compound. So what you need to do is figure out a sequence of reactions that will take you from what you have to what you want. Right? So you know, no mechanisms. You just want to have like, if I do X to this thing, I'll get this compound, and then I can turn that into this using something else, and then go to there. All right. So that's what I'm going to ask you guys to do right now. Open note, open book. These are all reactions you guys have seen this semester. So take a crack at it. I'll try to guide you along the way. Get some hints every now and then.
So you want the mechanism, obviously, right?
No, I do not want mechanisms.
Just what reactions there would be?
Just what reactions. So you need to show me the reagents, what the product would be, and it's going to be more than one step, all right? There's not a single reaction that will take you from the compound on the right to what you want on the left. So it's going to, huh?
Like this can have different answers.
Yeah, actually, I'm looking at it. I had an answer in mind. I've gotten in the habit of banging out notes before I come over here and then not putting them in my bag. So I was counting the carbons. Like one thing you always want to do is sort of take stock of how many carbons you have. You need to make a carbon-carbon bond, and I don't think you do in this case. And then, what's the other thing you asked?
Oh, I was just asking.
Oh, are there different answers? Yeah, so I had an answer, like when I write a synthesis problem for an exam or a quiz or a class, I typically make sure there's one answer. Right, as long as there's one, I'm covered. Nobody can come up to me and say, there's no way to do this, which has happened before. But then there's usually more than one way. And then it's often a combination of reactions where you can have wildly different reagents. All right, so see people scribbling away. I see some frustration. First, I wanted you to work at it for a little bit. Classically, in a synthesis, the way to work these is backwards. Right? So it's like if I start from here, I guess this is hard. If I was just plopped down in this classroom and told my office is in Salem Hall, right? I don't know where Salem Hall is. I would look at a map is what I would do. But if you don't have a map, like how do you find it? You have to have some idea you have to know something about Salem Hall and where it is in order to get there. Like I can go kind of an infinite number of directions out of here. So I need some guidance. Like starting here, what do you do with that, right? Like there's not much to do with that. So work it backwards. You were gonna ask something?
No, I just,
No, what?
I have an idea about what to do with.
I'll come look at it here in a second. Okay, so you got to make this compound. You've got an OH on adjacent carbons. So do you know a reaction that will do that? You do, right? So you actually know two reactions will do that. There's no stereochemistry shown here because that's not a chiral center. So you can do syn dihydroxylation, you can do anti-dihydroxylation. Either way. And this kind of goes to are there multiple answers? Yeah. So then we're going to use what's called a retrosynthetic arrow. And I don't know how much you'll see this. I feel kind of obligated to teach it to you. This is, if any of you become organic chemists, you'll use this a lot. If you don't, you will likely never see it again, with the possible exception of Orgo 2, which is why I'm throwing it in here. So the reaction would be that, right? So some sort of dihydroxylation. And what this retrosynthetic arrow is, it's a big fat arrow that points the wrong way. This looks like a reaction that you would turn the diol into the alkene. That's not what it means. This fat arrow actually means makes from this, right? This fat arrow means we make the diol from the alkene. It's called retrosynthetic arrow. You can use it or not. I'm not gonna like I said, there's one of these problems on the final project. So you can use the retrosynthetic arrow or not. It doesn't really matter. Okay, so what I was gonna say is when I'm in the lab, I pretty much do this the whole way. Because what I have available to start with is not a single compound. I have basically anything I can buy, anything we've made in the lab previously, anything I happen to know my colleagues have in their lab. I have a whole bunch of things. So it's sort of like, I need this compound, well, I can make it from that. Do I know anybody that has that? Can I buy that? Have I made that? If not, well, I gotta make this compound. What reactions do you know that would make this compound? Go back. On a synthetic problem in class, kind of double check it with your starting material, right? Can I make this compound from that compound? If you know a reaction that will do that, you're done. If you don't, keep working backwards from here until you find one. All right, go ahead and take a copy. You think you have a solution? You're good? Yep. Yep. So keep rearranging, right? There's already, you would need to put something. You're just moving.
I see.
There's got to be.
If I had like something out here that could grab that.
It's not a matter of grabbing hydrogen. It's that you can't make a new bond. That carbon's already got 4 bonds.
Okay, so I just need to work on the stuff to get it
Yep.
together.
a shout if you have a question. I'm trying to remember the second one I did. If you have an answer you like on the first one, you can try that second. Yep.
I guess I'm struggling to get from the as I get the dehydroxylation. I'm struggling to get from the start to what you would dehydroxylate from.
Well, so you're trying to make this from something, right?
From
So right now, you're just trying to make this, like, what reactions do you know that would make this compound?
Mercaptan product. So I'm going to give you the anti-mercaptan product, right?
But that would be in addition to the alkene. So think about the direction we're going. The actual reactions, we're trying to start here and go this way, right? So this reaction, the reaction that's shown here, this would be the starting material, this would be the product. All right, so you basically need a reaction, some reagents that get you here from
Oh,
X.
would that be like an elimination?
So it would be an elimination. And this again is what I mean by there's a lot of different answers here. So what kind of elimination is it? It's a Hoffman elimination. You're getting, right, this is a disubstituted alkene, getting the trisubstituted, this won't do it for you. So a lot of the eliminations that would make this compound, so the corresponding Zaitsev elimination would be this one. And that one you can't dihydroxylate. Dihydroxylation of this one, you get an OH here, but also an OH here, which is wrong. So the elimination, well, actually you could do it Zaitsev. So this X could be say a bromine there, a leaving group. All right. Actually, at this point, I'm putting a bromine here because I know the final answer. Right. This could actually be any sort of a leaving group. So that could be an OH. It could be a tosylate. It could be a chloride. It could be a bromide. It could be an iodide. Whatever. But if you do this, for that one, would have to be a Hoffman. So you need a bulky base is the answer here. Or it just occurred to me this would also work. You could use that bromide, right? You could have the primary bromide, and now any elimination is going to give us that double bond. So, yeah.
And this might be a leading question, but if you had a leaving group there, though, how do you How do you get the reactant to make that if it doesn't have an alkene?
So how do we get the leaving group on here? Is that what you're?
Yeah.
So, what's the reaction? I know you know the reaction. Anybody else got the reaction? So that would be a big, like if you don't know this reaction. So when I said there's a lot of answers, the first step is the same for everybody. Do you want me to, now that you're on the spot, you want to say it?
Yeah, sure. You have to radicalize it. So
Yeah.
you would take the original alkane and you would add Br2 and then light,
Yeah.
and it would knock off an electron and add a bromine.
Right. So this is the one reaction from chapter 10 you guys got to know. Radical halogenation. And so the question there, and yeah, like I said, you guys are going to sit there and spin your wheels. If you don't know that reaction, there really isn't a way to do it, right? All the chemistry you guys have seen this semester, acid-base, alkanes aren't going to do that. Chapter 7, substitution, elimination, you got to have a leaving group. Okay? If you don't have a leaving group, none of those reactions happen. Rearrangement, you have to have a carbocation to do a rearrangement. So, if you can't just say there, I mean, you can't, so here, I'll talk a little bit about how you can answer these questions. Like if you had a primary carbocation there, you'd get a rearrangement, get the tertiary cation, and then bromide might add in. But there's no way for that alkane to just make a carbocation. So if you guys, if you see a synthesis problem that starts with an alkane, you essentially have to do a radical halogenation. That's chapter 10, and it's going to preferentially put the bromine on the tertiary position, right? You're gonna put the bromine on the most stable position, the most stable radical. So that has to be the first reaction for all of these. Yeah.
So, if you do the radical reaction, will it give you the one that you wrote in green as well as the one you wrote in black?
No. Yeah, sorry. There really is no way to make that one in green. That's a good question. The one in green, if you could make it, would give you the alkene. But the only reactions you guys know that would make this compound in green start with this blue alkene, which is what you want, right? If you have the blue alkene, you don't want to, and I will see this, okay? So, again, I'm not laughing at you guys. Hang on, just before I tell you that. Mark, you had a question?
I was just going to say, I don't think this is one of the mechanisms that we learned, but just out of curiosity, I was thinking another way to maybe do it would be if there's some sort of thing as like a reverse hydrogenation.
There is. This essentially is a reverse hydrogenation. You're functionalizing an alkane. So it's a reverse reduction. It's an oxidation reaction. Yeah, there is. There is, but they usually aren't selective. So his suggestion is just go from the alkane to here, right? You guys know the reaction to go from the alkene to the alkane. If you take this blue alkene, treat it with hydrogen and palladium, you get the black alkane. The reverse of that also uses transition metals, and it's not a real good reaction. It's very unselective. You'd probably put alkenes in kind of all over, and it's way beyond the scope of this class. But yeah, that reaction can happen. So what I was going to say is, I will see that, like and certainly on an exam. You know how on exam 2 is like the first time you guys drew mechanisms on an exam. So the pressure gets to you, arrows start going crazy. Like I've seen a lot of crazy mechanisms. First time you guys do a synthesis problem on an exam, there will be some crazy answers. On the final project, you should be able to think of, take a deep breath. When you guys, it's kind of like writing a paper. When you guys think you have a synthesis, again, if you put this off till the last night, you just have to turn it in. draw your synthesis, set it aside for 48 hours, and come back and take a look at it. Because you'll do some crazy stuff. And I have seen people do like, get to here and then do some reaction to it and then eliminate it to get back to here, just kind of keep circling around. Like, you don't want to do that. You want to, like I said, you can't make this green bromide without making this blue alkene. And you don't need to do that reaction. If you got the blue alkene, you're there. Right? So just take a long look at it. Okay, so the answer here, so back up. The answer would be start with the alkane. Let me make sure the camera's going, since I'm finally going to tell these poor guys that sat there for 20 minutes. All right, start with the alkane, do a radical bromination. That will selectively give us a bromide on the tertiary position. Right. Now, this has to, and also, if you see one of these on an exam and you're like, I know I need to do an elimination, I don't remember how to do an elimination, I know it's got to be Hoffman, I don't remember how to get the Hoffman product, write Hoffman elimination. Right? That's not going to be full marks, but you will get most of the credit there. Like if you did all of this, if you have the right reagents here, the right reagents here, and all you say is Hoffman elimination, and I can't remember what the reagents are, that's like 9 out of 10. You basically saw what you needed to see. What you would use here, like I said, is a bulky base. So this is going to be T-butoxide or larger. Anything bigger than T-butoxide would do a Hoffman E2. And then, like I said, up here on the final answer, or the final reaction, right, this is going to be you've got a bunch of options. So one option is osmium tetroxide. And honestly, if you just write OSO4, I'd give it to you. The way this actually goes is osmium tetroxide and then sodium hydrogen sulfide or whatever. Or, on the other hand, you could do MCPBA and then either acid, aqueous acid, or hydroxide and water. Right. So again, like I said, for this particular reaction, for synthesis, the radical bromination has to be the first step. It's the only way you know to functionalize an alkane. The second step, the elimination step, you've got your choice here. You can do any large base, T-butoxide, triethylamine, something bigger. And then for the dihydroxylation, could be any of the dihydroxylation steps you know. Mike.
Would you want us to write a temperature for the elimination?
No. Why do I not need a temperature here?
I mean, if it's T-butoxide, it's going to be elimination, so it's too big to do substitution.
It's true. What's the other?
It's a tertiary.
The halide, the bromide's tertiary, so it can't do SN2. So if you want it, like, tell me a high temperature. That'd be fine. But and you guys, having said that, you should definitely know that higher temperatures favor elimination, right? If you're looking at substitution versus elimination, higher temperature favors elimination. But you can't do SN2 here. So as long as you've got a strong base, it'll do E2. And it's just a question of is it Hoffman or Zaitsev. All right, so give the one over there a shot. It's a little harder. Yep, sorry. It's not a terrible idea. You get the OH, but you wind up with an aldehyde, not a.
Really?
Yeah, this is a really bad. This is Orgo 1. If you make that aldehyde, there's a lot of different. You'll see in a little